Welcome back to the final video in our series of the Coulomb's law exploration. The final video in this investigation allows you to compare your results with our own. We're going to talk about the assumptions we made, and then you can compare them to yours. Doesn't mean that your assumptions had to be identical to ours, but we'd like you to listen to them and think if they're reasonable, and also to reflect on your own and see if they were reasonable. We assumed that we could treat each balloon as a point particle at the center of each balloon. So we assumed that the center of mass of each balloon was essentially in the center. We assumed that the two balloons had identical mass and identical amounts of excess charge, which allowed us to say M1 is N equal to M2, which means we didn't have to use this equation separately for each balloon. We assumed that Q1 is equal to Q2, which allowed us to combine the product of Q1 times Q2 into Q times Q, or Q squared. If we didn't make this assumption, this is probably the critical assumption, we would have been stopped in our track. We would have had too many unknowns as we tried to make these two equations work together to find the charge. If you did not make that assumption that Q1 equals Q2, this critical assumption, you probably were not able to actually come up with an answer to the charge, and you were stopped right in your tracks. If that was the case, what we'd like you to do is actually to pause the video here or go out of the video, make that assumption, and go back and using your numbers, calculate the value of Q. Doesn't have to be identical to ours, but you probably couldn't do anything if you didn't make this assumption here. This is sort of the critical assumption to be able to proceed. If you didn't make it, you didn't do anything. And we do really want you to calculate the value of Q from your data. So please pause the video if you didn't do that and make those calculations and then come back. Well, hopefully you have some value of Q now calculated either previously, or you stopped the video and made the assumption of Q1 equals Q2 and moved on. We also assumed that delta Y was small compared to L and could be ignored in our calculations. You'll see that in a moment. And that delta X, this distance here, the displacement in the X direction, was exactly half of this distance here, the distance between the center mass of the two balloons. We based that on some symmetry arguments, and so those are the assumptions that we made. We used the mass balance to determine the mass of the individual balloons, so it's 10 grams for the 4 balloons that are on the scale. Allowed us to conclude, again with assuming the masses of the two balloons were the same, the mass is 0.00250 kilograms. We used a half-meter stick down on the bottom of the picture to make an estimate for the length of the balloon from the pivot point to the center of the balloon, which is what we did, and we have approximately 0.75 meters. We took the distance, the separation from center to center, from here to here would be 30. We didn't think it was quite that. We estimated that to be about 28 centimeters, or 0.28 meters. Summarizing our assumptions, the measurements and the physical principles below. The mass of the first one was equal to the mass of the second, 0.00250 kilograms, a length of 0.75 meters, distance of 0.28 meters. The D was 28 centimeters, so again, that assumption that delta X was half a D, we said that's 14 centimeters. We're going to put in eventually delta Y is 0 in here, and the fact that Q1 and Q2 are equal. We'll set the two equations equal to each other and rearrange the variables, solving for Q. Remember Q1 equals Q2, that would be Q squared. Remember delta X in our assumption is half of D, so delta X is D over 2. Delta Y is 0. Placing all of those assumptions and approximations in, our equation simplifies to Q squared equals, there's the D squared times D over 2, D cubed, there's the 2, and the delta Y goes away, so the denominator is 2KL. Take a moment to see that you agree. Plugging our values, our estimates, which we doubt would agree exactly with yours. Hopefully they're somewhat in agreement. If you didn't go to the center of the balloon, you might have a larger value for L and a different value for D. Our masses should pretty much be in agreement, however. You may have made some estimate somehow for delta Y and not assumed it was 0 and actually put it into your equation. So here's all our numbers with the units in the equation. And so we have a value of Q of approximately 2.0 times 10 to the minus 7th coulombs on each balloon. The net excess charge, either positive or negative, we still don't know, of 2.0 times 10 to the minus 7th coulombs. From our previous work, we stated that a coulomb of charge contains approximately the charge equivalent of 6.25 times 10 to the 18 elementary charges. That's the charge on either an electron or a proton. And using that, we can convert the 2.0 times 10 to the minus 7th coulombs to elementary charges, and it comes out to be 1.2 times 10 to the 12th elementary charges. 10 to the 12th is, let's see, 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion. 1.2 trillion elementary charges in either excess or deficit on each of these balloons. Trillion. That's a lot of electrons being moved around. Well, the question still remains, are these balloons charged positively or negatively? That would depend on how we charge them, what we use to charge them. It could be either case. Can you suggest, and if you look at this diagram, there may be something in the diagram that would allow you to suggest an experiment to answer this question? What do you think we did? Little hint there. Well, here we see the professor holding a rubber rod that was rubbed with fur near the balloon. Please record your observation, what you see the balloon doing, and then make a claim on whether you believe the balloon has an excess of negative electrons or a deficit of electrons. Make sure your claim is based on evidence and the model, our electrostatic model that we've studied in these past units. Well, we hope you've enjoyed this series of slides and movies on Coulomb's law. This concludes our unit on electrostatics. We studied Coulomb's laws, Newton's laws. We looked at the typical charge that was on an object through static charging, for instance, in rubbing your feet on the floor and zapping your friend, or rubbing a balloon on a sweater and having it stick to a wall. We hope you enjoyed it. Bye-bye.